Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce JangWoo Kim from Carnegie Mellon, who is a graduating doctoral student who's here on a job interview. I've been very impressed by JangWoo so far, so I'm very much looking forward to his talk, which looks at the implications of process variation for SRAM memories. And this work has a lot of momentum behind it. I'm very excited to hear about it. JangWoo worked for Babak Falsafi at Carnegie Mellon. Is a good personal friend of mine, and he comes very highly recommended. Babak said he was so good that he could handle any questions we asked, so just let the guns blast. I'm kidding with that last part, but I'm sure that will be the case. So without further ado, we're looking very much forward to your talk. Yeah. So thank you for coming.
Good morning, everyone. My name is JangWoo Kim, and thanks for coming to my talk. Today, in this talk, I'm going to explain one of my work which improves memory system reliability and manufacturability using efficient multi-bit error correcting code. So when you say reliability and manufacturability, we are talking about errors, right? So what are those errors in devices? So errors can be broadly classified as a soft error or hard error by the nature of the errors. And hard errors can be further classified as manufacture time errors or runtime errors. So here I'm showing three cases of errors. So first one is a manufacture time hard error. So this is mostly a result of a device variability. So some transistors are faster than some transistors. And runtime soft error, we lose values in the transistors. So basically it can be, if we keep using this device, this error doesn't reoccur, but there's a possibility of losing values in the runtime. Runtime hard error is basically where our device wear out or some device getting broken during in field. So real problem is these errors occur in increasing frequency and increasing scale. So how those errors occur in memory systems? So previously we used to have a small number of errors, and each error occurred only a few bits of small scale errors. But as we go to more deeply scaled technologies, and everything gets smaller, and then we apply lower voltage. So we're expecting many more errors, and each error will affect larger scale information loss. So we need a really mechanism to tolerate those increasing frequency of errors and larger scale information loss in field. Yes?
So are you asserting that a high energy neutron knocking a silicon atom out of the lattice can actually cause multi-bit errors in SRAMs?
So that's one of the reasons. Okay. These days, we are seeing up to 4-bit failures from single energy particle failure, right? But by decreasing the dimension of both dimensions, we are expecting up to 8 to 16. That's from what industry said. And that's only one reason. Sure. And the other case is even soft error can propagate through the sharing well or substrate. That actually secondary impact, and this is observed in the real world. So actually it is up to 16 cells at this technology. It's a rare event, but that could happen.
So it's a cascading effect of silicon atoms?
Right.
Going through multiple cells in the lattice?
Yes.
Okay.
As long as they share the substrate and the wells.
Right.
So to mitigate the problem, you can put more contact, or we can separate cells. So that's the circuit level solutions.
Right.
But this is only about soft errors. I'm not talking about just the soft errors.
I understand.
Yeah.
So you've got the little lightning bolt. So
right. So, yeah.
That sounds great from a physicist's point of view. You have a particle detector here.
Particle detector.
Yeah. And eventually we'll have a neutrino detector.
Well,
that's
really valuable then.
Except right I haven't thought of it that way. So conventional protections assume only a small-scale errors and a small number of errors. Here I'm showing two cases of conventional protection. The left figure uses a few redundant rows to repair the defects, and right figure uses conventional single-bit error correction code and combined it with a two-way bit interleaving. So if you combine one bit ECC with two-way interleaving, it can correct up to two cluster bit errors. The problem is as we repair, after we repair certain groups of defects using existing redundancy, there's the remaining errors which requires another protection. And for the soft errors, I mean, so after we correct up to 2-bit clustering errors, if we get the large errors, we cannot correct them. So conventional protections techniques cannot repair many errors or large-scale information loss. So natural way of dealing with this problem is probably we can increase error coverage of existing scheme. So first one, we can probably apply a multi-bit ECC, or we can increase the degree of interleaving, or we can just put more redundancy. But obviously, if we put multi-bit ECC, we actually put extra coding logic, extra space for check bit, so that's significant VLSI overhead. And for higher degree of bit interleaving, actually it can correct up to only cluster bit errors, or it's very power inefficient. It can also incur very high amount of power. So I will come back to this point in later slides. And obviously, if you put large redundancy, that's area. It takes lots of area. So my solution is we apply I'm proposing using a 2-dimensional protection inside of each memory array. So here I applied a conventional protection, similar to conventional protection as the first line of defense. So for this one, I assume we can detect errors in real time, in runtime at minimum latency. But we can also apply a large-scale coding, which applied only once and only to the large-scale data. So by have this strong coding, we can correct large-scale errors. So basically, we are splitting the responsibility of the error detection and correction to two different codings. Any questions? So by combining this common case single coding or more sophisticated complex coding, but this is done in background, we can combine them, we can get synergetic impact over higher error coverage at very low overhead. So my
I'm sorry, quick question. If you were only concerned about soft errors and not hard errors, would a feasible solution be protection through packaging, basically hardening through packaging?
Okay. You mean the circuit technology for hardening?
Yeah, through packaging.
Yeah, I mean, so this is always about the cost and the what we get and how much we pay, right?
Certainly.
Yeah, so obviously some space applications, I mean, they can put like a certain hardening technologies, but always a mass product, the commercial product, don't have that much protection in terms of circuit. So they actually prefer putting a single bit error correction code and some way of interleaving. This is a more popular choice.
Right. So alpha particles, my understanding is that alpha particles are easy to shield against, and so people have sort of done that.
Right.
But the high energy neutrons require.
So alpha particle is not a problem anymore. We already solved that problem using circuit techniques. That's already baseline. But we are mostly worried about the high energy particle coming from sky. But still, you can do certain technology. I mean, make certain hardening technologies, but that's not a popular solution. So my application is 2-dimensional error coding in a cache. So we apply a horizontal code. This is a simple error detection code, or optionally we can make to correct a single bit defect, but assume this one as error detection code for a moment. And we put vertical code at the bottom of the array. So basically vertical code is also simple code, but you can see as a whole picture, then when you combine horizontal code and vertical code, that becomes a strong code. So I assume certain amount of defect, and since we have a high error coverage, we only repair using a redundancy using only for the only large scale defects. And we also experience soft errors during runtime. When we use both coding, then we can correct all those errors. So we showed, so when you use the 2D error coding, we can get very high multi-bit error coverage at very low overhead, and it can be used for defect tolerance too.
Can you talk about the? Are you going to talk about the downsides of this approach later?
Yeah, yes, of course.
All right, so then
Yeah, there's enough free lunch, right?
Why do you need to be in the background when you're talking about
So usually when we put the value to the memory, we have to compute extra check bit. That becomes extra code, right? So for horizontal code, when we write something, we update the horizontal code. For vertical code, we also have to update the vertical code. This is related to Doug's question. So so for this vertical code update is performed at the out of critical path of normal operations. That's what say background. So this vertical coding update is done. How can I say? Later. It's not later. It's actually it can be done later, but it doesn't affect normal operations.
Okay.
Actually, I'll come back to that one.
Well, it's done incrementally.
Yes, incremental. I actually can pipeline. I mean, we can pipeline this updating logic, and it completely out of separate from this memory, normal memory read and write, and.
Okay, so it's just the latency because.
Well, the bank is not structured in a way that makes getting all of a column easy. That's the problem.
Okay.
Right. When you read out a row, you get the whole horizontal row, and I should.
Actually, your answer is better than my answer. Yeah. So.
I'm old and gray.
Yeah. So it's a horizontal and vertical code. Actually, this is considered as a product code in coding theory. So to update vertical code and horizontal code, normal way is we read everything. We update every whole array at once to compute. But that doesn't happen in cache because we only modify single line, right? So to simple way to update vertical code is we get the difference from when you write horizontal code, we get the difference between old data and new data, and that difference applied to the vertical code. That update is done background of normal operations. That doesn't affect normal operation, normal read and write in memory.
Okay, so you can wind up with stale codes then.
I'm sorry?
I mean, can you, so there's a window where you haven't updated the vertical code.
Right. So actually there's an overhead. I mean, we actually have to read all the value, right, before write. That becomes a really, so that actually incur the extra port bandwidth. So I'll come back to that point. That's the really overhead of 2D code coding. Right. Right.
Of course, this works really well with DRAMs because you do the refresh and you read it all out anyways. But
Actually, I mean, some processors do that for the cache too,
yeah.
for the partial ECC write.
Yeah.
So when you write a small byte, you have to read the whole data to compute a new ECC. So for example, latest Optimum processor, quad processor, they actually do read before write every time for read. And also Alpha did that too.
Yeah, but they're not going through every row if you do a read. That's much
Yeah. Right.
So do you wind up with a problem if there's been an error and you do an overwrite then?
I'm sorry?
Well, so on reads, presumably you're checking the
Errors.
horizontal code.
Right.
If when you do read before write, do you check the horizontal code?
Yes.
You do. Okay.
Right. Of course.
So
Yes.
if you just read that bit out, the bit
Right.
was wrong.
But this is yes, of course. If we find that we found the errors, we have to correct them right away. Right. But the message is we only detect errors for these configurations. Okay. So I'm going to briefly go over the existing protection schemes and why it doesn't scale. Explain why it doesn't scale. So this is a typical way of making multi-bit ECC. So we can start with a single-bit ECC. We take a 64-bit data, and we compute the 8-bit ECC bit using our XOR tree. This is an implementation of some multiplication. Then we get the 72-bit ECC code. So this is already significant overhead in terms of power and area. If we want to increase the error correction coverage, we have to duplicate, linearly increasing this circuit overhead and check bit area overhead. So obviously we see size of word increase pretty quickly, and it takes lots of area and power. So these two graphs actually shows what's the overhead of energy overhead and storage overhead. So for in the x-axis, I'm increasing error correction strength from 8-bit error detection code to the 8-bit error correction code. And when you apply ECC to different code size, we get the linearly increasing storage and energy overhead. So that backs up my intuition from explanation from previous slide. Yes?
I have a question. So it seems to me like as you increase your width, the width of the word,
Right.
you would increase your energy overhead, but decrease your storage overhead.
Yes. So this is the nature of coding. If you put a specific coding to large data, the relative area of the extra check bit decreases.
But the relative energy to compute it increases.
But also, this energy increase a bit line driving energy, right? So now we have a few bits. So we actually saving some power in the bit line driving.
I see.
Right.
Okay. I was wondering why the crossover
Yeah.
there. Okay.
So another way to protect multi-bit soft errors is put a higher degree of bit interleaving. So this is a simple illustration of bit interleaving. So we take for 4-to-1 bit interleaving, so I call 4-way interleaving. We get 4 words and we interleave by bit. And so the beauty of this coding is when you get 4 cluster bit errors, it is manifested as single bit error per code word. So this is this is actually used in every processor these days. But since we are making a long word line, every cache read and write, we have to drive all the lines. So that's the limitations, and that takes lots of power. So this is energy overhead caused by bit interleaving. So so as I increase a degree of interleaving from no interleaving to 62 interleaving, it actually increases up to 600%.
Can I ask you, can you go back? So why couldn't you put the support in the array to only read out and drive the lines for the interleaved word that you want?
Actually, it's a timing. So we actually pre-charge everything, and we just take the corresponding word. If you put extra circuit in this timing critical process, that takes much time. Actually, I might miss the question.
No, you understood the question.
Yeah.
Just doesn't seem like the timing is that critical. Putting a transistor on the SRAM, putting a transistor on the driver for the pre-charge. It seems like you could turn that on or off in advance and save a lot of the energy.
Actually, it's not that simple. Let me see. So basically, we are making another layer of multiplexing.
Yeah.
Right? So actually, that can take a lot longer time than we think.
Okay.
Yeah. Okay, so if we put large redundancy, after we map the the fundamental problems about the redundancy. So nature of a defect is small scale defects. It's many defects, but randomly distributed. For redundancy, hardware redundancy we conventionally use in memory is granularity of lines, rows, or arrays. So if we keep repairing small scale defect using larger scale lines and columns, then we end up with wasting lots of area. So this graph shows the cell defect rate tolerable by the given amount of redundancy. So here, 10% means we gave 10% extra area as a redundancy purpose. Then for that purpose, even with that amount of redundancy, we only tolerate up to 0.2% defect rate. So obviously, we are wasting a lot of area. So I'm going to show how 2D error coding solve this problem and how to achieve a multi-bit error tolerance. So again, 2D coding architecture is based on horizontal code and vertical code. And this horizontal code and vertical code are basically error detection code. So this can be implemented as interleaved biparity code. So this is a fast code. But when we combine those horizontal code and vertical code, we can correct large scale errors. So so we should understand why 2D coding works. So when we apply the ECC coding mechanism, we have to decide the coding strengths and the data size. For example, conventional code apply the simple coding, such as a single bit error correction code, to small data. So in that way, they achieve a fast error detection and correction latency. But obviously, this is simple code, so the error coverage is limited. But 2D coding is actually take this approach as a single fourth dimensional code. And it adds a second dimensional code by combining strong code and large data. So basically, we put product code to the entire array. So, and then this is only used for correction. So long latency doesn't become problem. By added, we only get a synergetic impact of low latency and high error coverage. So that's why 2D coding works. So let's see, go over how 2D coding actually detect and correct errors. So during read, horizontal code will detect errors. It doesn't know exact locations, but it can know this row has errors. Then by combining both vertical code and horizontal code, it can reconstruct the whole lines. So basically, our error correction coverage is based on the how much area we allocate for the vertical code. So do you have any questions? So let's see how 2D coding make a scalable solutions. So I'm starting with 4-bit error coverage area. So we combine the 4-bit ECC with 4-bit interleaving. So you can correct up to 4-bit errors. But if we want to increase this error coverage to 32-bit, then we have to increase degree of interleaving and strength of error correction code. So here I'm assuming a 4-bit error correction code and 4-bit interleaving. So in that way, we can correct 32-bit errors. However, we're making extremely long word line, so this takes lots of power. And we're also making large area for 4-bit ECC check bits, so that takes extra coding and extra area. So instead of doing this, we can apply 2D coding. So basically, we're not changing anything about memory array. And we just simply replace existing simple 1-bit ECC to 8-bit EDC. So basically, this is a similar overhead. And we only add 32-bit EDC. That's error detection code at the bottom. So our overhead is only a small area located at the bottom of the array. So again, actually, I'm going back to the original question. So 2D coding is not free. I mean, to update vertical code, we have to know the difference between old data and new data. So that means every write becomes read before write operations. But the so read before write operations basically incurs extra read to the array during normal operations. So that can incur extra port contention. So theoretically, it can affect the normal operation performance. But in real world, read port contention is found as not that serious problems. For example, some architectures already support read before write operations. This is mostly for partial write over ECC. And for those architectures, we don't have any 2D coding doesn't incur any extra bandwidth. And we can also use a well-known technique such as the port stealing. So port stealing means we split read part and write part of read before write operations, and we issue read operations using idle cycles. So because we don't have to perform read and write back and as a back-to-back operations. And for popular multi-thread architectures, this latency can be hidden just by simply scheduling other thread. So throughput doesn't affect much. Do you have questions?
There's lots of things we could do if we had lots of threads.
Yes, of course. So I evaluated the 2D error coding using Flexus. That's our full system simulator developed at Carnegie Mellon. So I have two baseline, chip multiprocessing baseline. Well, first one is a fast CMP. So fast CMP means we have fat, wide audible quarter, and 4 audible quarter superscale processors. For lean CMP, we have a simple cores, but we have many of them. So we have 8 cores. To get the high IIP, we put the 2 ports on L1 cache, and then L2 cache is large. So this is basically similar to Intel Montecito processors. For write one, we tried to model Sun's Niagara processor. So we have a small L2 cache with many banks, and there's only 1 port for L1 cache because this is multi-thread processors. So we also we implement 2D coding in entire cache hierarchy over these 2 baseline systems, and we evaluate using a 6 workload. So we basically evaluate using a 3 server workload and 3 scientific workload. So this is performance overhead of 2D coding during normal operations. So in other words, this is overhead what we pay from the extra port contention. So we are not assuming. We are assuming that baseline doesn't have the read before write operations as a baseline. So for each baseline, there's a 6 workload, and the y-axis is performance overhead normalized to the baseline system which doesn't use 2D coding. So higher bar is a performance loss, higher performance loss. And first bar is the performance overhead when we apply 2D coding to L1 cache only. And second bar is the same, but this time we enabled port stealing. And third bar is the performance overhead when we used 2D coding to L2 cache. And fourth bar is when we apply 2D coding to both L1 and L2 caches. So big mess. Second bar? Yeah, so we protect only L1 cache using 2D coding, but this time we apply the port stealing. So what we do, as I explained, what we do is when we see the write operations, we take address of that operations, we issue using idle cycles. So there's a certain distance between read and write part. So as you see,
So why do you see the performance loss when you're doing port stealing?
we are saving lots of performance overhead, but this is not the perfect, right? Sometimes we don't have idle cycles,
Okay.
right?
And then you're actually...
the store queue is full then, yes. So what we see is overall performance overhead is really small, as is 3%. But for really a memory-intensive application like Ocean, this baseline already takes like a half of a bandwidth without 2D coding. So incurring, adding 20% extra read, actually it was 20%. 20% extra read incurred high performance overhead as 10%, yes.
How large is the working set?
I'm sorry?
How large is the working set?
How large a working set? So I don't have exact number for iCache, but what we know is a server workload. We are spending our misses, half of miss was from iCache miss. So basically that's a typical behavior of a server workload. So iCache doesn't have the whole instruction footprint, so we have many missing out to cache. For data, so data works out. So we see reasonable amount of misses. I mean, I also don't have a specific number. Actually, so this is actual breakdown. So during 100 cycles, this is how much time is how much time spent from each category. So this is L1 cache and L2 cache, right? So we are spending this much time. White bar is read data, L1 cache, and L2 cache is data, and this stripe is instructions. So. Where I was here. Yeah, so for Lean CMP, this multi-thread architecture, so we hide this latency and we get the almost no sensitivity in throughput. So this is implementation, the VLSI overhead of 2D coding compared to existing schemes. For this graph, we assume we want to achieve a 32-bit error coverage. Right? So 4 design points include 2-dimensional coding, which use simple error detection code in both directions. And rest of the 3 design points are combined different degree of interleaving and different strengths of error correcting code. So for example, when you combine 8-way interleaving with 4-bit ECC, then we can get 32-bit error coverage. Okay. So and first bar is, so every overhead, first bar is a code area overhead. This is how much area we spend for allocate for the extra check bit. And second bar is error detection latency. So this is coding latency. And third bar is how much energy we spend, we consume.
What's the normalization point?
So normalization point is a 2-way single bit error correction code. So okay. Yes. So the big message is 2D coding is almost similar, has almost similar overhead to conventional 2-way single bit error correction code, even though we achieve 32-bit multi-bit error coverage. But other design points have to consume a lot of power over a large area, right? Actually, one thing I want to say is this is also a huge improvement in terms of latency. So for certain microprocessors cannot use ECC in L1 cache because even L1 single bit error correction is slower than, it was too slow for them. For this one, we can use error detection code during the error-free mode. So we can actually implement 2D coding without incurring much extra latency, even compared to single bit error correction code. So I already showed this graph. So we have a given amount of redundancy for 4 megabyte SRAM, and red one was a defect tolerance. If we apply 2D coding, at this time we assume that horizontal code can correct a single bit defect per word. So we get huge improvement in defect tolerance. So this is like if we have a 2D coding with 0.2% redundancy, we'll achieve the same defect tolerance as having 10% redundancy. Yeah, this is random, and actually, yeah, this is random. I'm just showing the. some potential here, the first line potential. So I show that 2D error coding can be built to achieve multiple error tolerance at very low overhead. And I also show that 2D coding can be used for defect tolerance if we have error correction code as horizontal code, right? So
Can you go back for a sec? I want to make sure I understood that.
Mhm.
So why is, I'm missing something fundamental here. Why is this a higher cell defect rate better?
oh, this is a tolerable defect rate.
I see. I
Yeah.
see. So
So-
you're already under your bar,
Right.
and you're just saying these are both good solutions, but you get better latency and power.
Right, right.
Yeah. Okay.
So the question is, if we are going to use 2D error coding for variability tolerance, defect tolerance, so what we should know that what's the defect rate in the future. Also, we should know what's the error correction strength required for that kind of tolerance, and also we should know how this tolerance can be translated as yield, performance, power, or stability. So next we are moving to the variability tolerance of 2D error coding. So what's the variability, right? So now we are having for 65 to 45 nanometer region these days, and we are moving to 32 and 22 nanometer regions. So we are expecting to see high device variability, right? Even two transistors sitting next to each other will have more than 30% difference in terms of power and latency. So we are expecting to see many different kinds of device variability, so such as unstable cells. So we lose value during read access, or some cell is really slow, and some cells taking too much power during idle time. So what we can do is we can just discard the chips which has these bad cells, right? So that is really, I can tell this number, but I mean, they say they are like losing lots of money by discarding these chips in the industry. And also what you can do is you can repair using certain redundancy, or we can just ship the chips which runs at a lower frequency or just take more power, right? So this is a typical processor binning. So big message is it's really difficult to scale SRAM for future technologies. So this is a typical yield curve. So what I'm showing here is a histogram of 5,000 SRAM chips, and x-axis is the read latency of each chip, y-axis is count. So every yield graph it just looks like this with a long tail at the end. So what I'm showing here is if we want 100% yield, we make a cut at 3 sigma point, right? If we make the cut, most of the chips that can be actually faster than this yield cut point. But if we move this line to the left, we can make a chip faster, but we are losing a lot of chips because this failing the target. Okay? So really important thing to note here is yield is not just one number. So we have a trade-off between acceptable yield and acceptable performance. And this is not just the performance. It's the same story for performance, power, or stability.
Can't you just measure them, label them differently and sell, slow, medium, and fast ones? I mean, I think that happens.
So actually, I have the same question from the Intel, and they said potentially we can do that, but the reason we aren't doing it, we are spending too much time to testing each chip and the label each one. Yeah, actually, these days the cost of a chip is die area and then the time to market. Right? These days, we are already spending half of the time for the testing.
It's actually cheaper to just test them once and throw them
Yeah.
out. They're not binning and to sell.
They are doing binning, right? But they are doing binning, but they are doing very coarse-grained binning. Sure. So 2 gigahertz, 1.8, 1.6, yeah, that exists. But fine-grained one is really hard.
Well, it's also hard because you have so many structures. I mean, if you just had one, it might be easy to test for, but
Right.
and you've got to make sure that you don't miss something. So it's dangerous to do the fine-grained stuff.
Right.
Okay, so I already gave a hint that we can use a multi-bit error correction code to tolerate these variability errors. So suppose that we have a multi-bit error correction code. We can use some strength of a code to repair, to mask out these bad cells, right? So then we can get the higher yield and performance and power, right? Since we are repairing these bad cells using error correction code, we don't have to use much large amount of redundancy. But we also need some portion of multiple error correction code to support runtime reliability, right? This was a huge challenge for industries. I mean, some people already said we can use ECC for variability tolerance, but they gave up because they cannot give up the soft error tolerance in the field. So assuming we have multiple error correction code, now we have to know how much potential is there. So I modeled, I measured the potential multiple ECC for variability tolerance using circuit level simulations and modeling. So I modeled intra-die variations. So intra-die variation is the random variation existing in the die, and this is a major source of variation in the future. And this is a basic combination of pure random mismatch and some spatial correlations among the mismatches, right? And I designed a 5-cell design point, SRAM cell design point. So 45 nanometer baseline is existing baseline cell. I twisted them for the 20% higher density or 20% lower power. And then in addition, I evaluate 32 nanometer cell and 20 nanometer cell. So this is like an imaginary cell. Basically, we use ITR's roadmap to get realistic cell design point. Right. So, and also I assume the 60 standard cell is symmetric. So I implied intra-die variation to channel width, length, and then threshold voltage. And we measure the 4 characteristics from each cell. So we get the read latency, write latency, and read stability, and minimum voltage. So minimum voltage is basically, it tells how much power it can consume. So this is how I model intra-die variations. So there's a so we use I used excuse me, hierarchical variability model, right? So the bottom bar has like a random cell-to-cell mismatches, and the highest bar has like a die-to-die mismatches. We add all these variables, we get the realistic intra-die variations, and this is how it is typically represented in 64 by 6 cell array. So this is a case of threshold voltage. So different colors shows different threshold voltage. And as you see, mostly this is random, but there's a certain hotspots because of spatial correlations.
What was the middle layer?
It's so, do you mean color, right? What do you mean middle layer?
Well, you've got 3 layers that you're adding up there.
Oh, it's not 3 layers. I have like a whole, I mean, if you really, it's a lot of layers, right? I added like one bit to 1 bit, and there's a 2 bit to 2 bit. So I actually added everything to get this variability model.
How do you validate that? You know, has the literature already validated those sorts of models?
Yeah, this model was validated in the literature. Yeah. Yes. Actually, this is pretty new technology. Yeah. So using this variability model, a cell variability model, I conducted Monte Carlo simulations to get the 5,030 kilobyte SRAM chip. So what I did is I take each cell from that variability model and construct a 32 kilobyte SRAM chip. And the important thing is the worst case cell determines the performance of the chip, power of the chip, I mean, those things. Then we assume that single error correction code per word and a 5% redundancy for array. So this is a typical amount given to latest Intel processors. They actually use 30 megabyte. Among 19 megabyte L2 cache, they actually allocate 3 megabyte L2 space for the reliability. So this is actually the simulation number, the results from simulations. So I'm showing read latency and write latency of the 45 nanometer baseline cells as cell designs. So what we show is this black line histogram is the baseline. We don't use ECC or redundancy for variability tolerance. Blue line use single error correction code to tolerate variability errors, and the green one is using both redundancy and single error correction code. So important message here is this was why our 100% old 100% yield cut. But now I can move to this line yield cut to this point, right? Then we get huge improvement in read latency, or write latency, and we still maintain 100% yield, right? So actual number is not. So actual number is important, but it's not as important as this. So the thing is, now my chip can run at the best case chip of the previous graph, right? So that's a huge advantage. This is the same patterns for reduced stability or minimum voltage. So for example, we can move this line to this point. That means we can get the lowest power chip over the old distributions. Okay. So the message here is we really have to use ECC, and we should combine ECC with a real amount of redundancy to get variability tolerance. Okay.
The same thing, there's 3 different colors. Are these all using the same area, or the more area for?
So I'm assuming, the same area. I'm assuming that this single bit allocation code is existing for software tolerance, and FIFO redundancy is using for a runtime repairness. Just we are not using them for variability tolerance. So this is 4 other more aggressive cell design point. So we start from 40 nanometer technology with a higher density. So and the low voltage were 32 nanometer and 22 nanometers. So important. So what I'm showing here is 1 here is the operation point of 1 sigma point, and 5% redundancy is used for redundancy. So for future technologies, we have to use 5% redundancy to mask out really bad cells. So I will assume that 5% redundancy is used for variability tolerance, and we made the yield cut at 84% to get the reasonable operation point. Okay. Then we use ECC to correct rest of cells. The other bad cells. Then we get the this bar graph of each point. So I know this is hard to see, but what I'm basically showing is if I see the higher bar than 1, that means I improve the yield from 84% to 100%, and I also improve the performance, power, and stability. I expect questions. Okay. Yeah.
Maybe I missed something, but how do you tolerate variability with error correction codes? Is this variability in time or variability in space?
Variability in what is variability in space?
Basically, you have different latencies of different cells.
Right. So yeah, okay. So for example, latency, right? If this cell is too slow, right? So when you read the value, this value will contain the incorrect value. So you will be detected as errors.
But how do you know if it's incorrect if it's not changing in time?
Changing in time.
So the value you read over there will always be the same, right?
No, when you write it, you made a code, correct code assuming the correct value,
okay.
But that value changes in the memory.
Okay.
Or we actually start with the wrong value, but your coding algorithm knows that this value is wrong. So actually, this is not really different from soft error.
Okay. Well, you're coding it before you're writing it in.
Right.
Right.
Yeah.
And then when you read it out, you can detect
The coding itself is not tolerable to, it's not subject to variability errors.
Yeah.
Right.
You hope.
Yes.
So the following question then is the error correction scheme, which basically requires, assuming that you need both the vertical and the horizontal code,
Okay.
or just the vertical code at least.
Why?
There's no latency penalty for that?
Latency penalty.
So in order to do this sort of variability hiding, right?
Yeah.
Where you're on the fly.
Oh,
you
I see.
Cells to
Right.
live, but you're
So we are assuming 2D error coding for the large scale error correction, and we are assuming inline error corrections for variability errors. Yeah, I'm actually explaining that one in next slides.
Okay.
Right. Yeah, you are in the right page. So this is the redundancy overhead required. So this is showing the overhead required error correction strength and the redundancy to get achievement from previous graph. So what I'm showing is this block error rate from single failure source. So and these 3 lines has different strengths of error correction code, right?
So by failure, do you mean a variability-induced permanent error, or?
Yes. So when I say 30% here, from this failure point, ECC is happen to correct 30% of the blocks,
Okay.
right? So yeah. So this shaded region is like actual block error rate shown observed from previous simulations.
Wait. You said ECC corrects 30%, but isn't this the error rate? So it gets better as you go to the right, or worse?
Worse.
So it's the opposite of what you said.
No.
It's the fraction that ECC is not correcting.
Let me see. So it's okay. So we have to define the better and bad, right?
Yeah.
So when I say better, it means we have a less variability.
Block failure.
Right. But yeah, so in terms of a correction, how much we tolerate, yeah, that's gets to be better when we move to the higher ECC. But thing is, if you want to get the higher error rate, you have to correct many more blocks.
Sure.
Then you need a multi-bit ECC, stronger ECC. Basically, I'm trying to show that one in this graph.
I think you're answering a more complex question than I was asking. You really want to be at the left of the graph,
Yes.
right? And
Right.
it gets more expensive to support that as you go.
Right. That's the message.
Yeah.
Right. For example, if we have a 30% at the block rate, if we have a single bit error correction code, we have to allocate 40 to 50% overhead, redundancy overhead. Or if you have a double bit error correction code, we need only like less than 10% overhead. So actually, some other proposers showed this graph also, and what they did, they just disable 50% of a cache to get the same achievement. So what I'm showing is, it's really good to have a double bit error correction code dedicated for variability tolerance. And to get the soft error tolerance, we need additional error correction capability. So I assume that is done in 2D-dimensional coding. But we need to detect the third bit errors, right? Because if we have two variability errors and there's one soft error, it becomes a 3-bit errors. So we still have to detect these errors. So let's go back to ECC. So why is WB ECC not implemented in real world? I'm not in microprocessors, right? So let's start with understanding why a single bit error correction code is fast. So to get the 72-bit code, we take from 64-bit data, and then we compute through the multiply by ECC matrix. So this is implemented by XOR computations, right? So we get the 72-bit data, and then we store that value in the memory. When you read, we take that value and we do the similar process to get the 8-bit syndrome. So if this syndrome is 0, we know there is no errors. If there is a non-zero value, we know there is errors. So this is up to the error detection point, right? So if there's errors, how a single bit error correction code correct is it examines syndrome value, right? So we have a 72-bit value, and there's a single bit errors. So there's only 72-bit cases, right? So it's trying to match whether the syndrome, examine whether the syndrome matches one of the 72-bit error patterns. If that matches, we know the error locations. We just invert it. That's how it corrects it. So this can be done very fast, and it can be implemented as 72-entry CAM-like lookup. It's not really CAM, but it's like a 72 parallel circuits. Right? So why this is slow? Why is this so slow? Right? So for encoding, for decoding, it's almost the same. The only difference is a different size of error correction, decoding and correction matrix. But this can be done in parallel. So up to this point, error detection, coding error detection can be almost take same latency as a single bit error correction code. But then the problem is when we have errors, so now we have to assume 2-bit errors, right? If you have 2-bit errors from 79-bit data, there's more than 3,000 error patterns, right? So to make a really fast decoding circuit, we have to make a 3,000 entry hardware CAM memories. So this is not really done in any microprocessors. So in real world, what they do is they pipeline this circuit as a series of lookups, small table lookups, and multiplications. They take easily 100 of cycles. So now we are proposing using ECC to tolerate variability error during runtime. So this is always happening. So if you take this 100 cycle latency, it can be implemented. So now I just showed that why a multi-bit ECC cannot be built for variability tolerance. But there's a way to mitigate this latency if we know error locations. So variability errors, we know the error locations, right? So error locations, so if we know error locations, we can use erasure coding algorithm. So erasure means if there's errors in the code, the errors only occur in this place. So that's called erasures, right? So variability is just like erasures. Because during the test, or we know this value is wrong, and then we put this one in erasures. So there's equations for the d-mean, that's a minimum having distance of a code. And as long as we satisfy these equations, we can correct t-random errors and ER, a number of erasures, and we can also detect ED errors, right? So for conventional single error correction code has minimum having distance of 4. So this is a case of minimum having distance of 4, and we can configure many different kinds of error correcting code, and by just changing the configuration of error coding and decoding matrix. So we can make, for example, we can make a 3-bit error detection code or conventional single-bit error correction, double-bit error detection code. If we know 2 erasures, we can make the double-bit error correction, triple error detection code. I'm showing why this is a good idea.
Hold on.
Yes.
So I get all that except that if you can oh, never mind. Okay.
Yeah.
Right.
So what's the erasure coding algorithm? So we take an original word and put all zeros to these 2 locations and put the ones to all these locations, right? So each word has up to 2 errors now, right? But important thing is if you add up these E0 numbers, E1 numbers, it's always 2, okay? So in other words, at least one of these blocks will have less than 1 errors, okay? So what that means, if we put a single error correction code to each word, at least one will correctly get the original value.
Why is that a guarantee?
Okay. So when you put 0, 0 here, this block has up to 2 errors, right? And this block has also 2 errors. But it's only either one of each bit has 1 errors, right? So if you add up E0 and E1, we always get the 2, okay? So this is always 2, and each one is less than 2, so at least 1 is less than or equal to 1, okay? So I'm actually trying to make a very simple view of erasure coding. There's actual mathematics behind this.
Right. You're copying the word and you're replacing the bits. In some sense, you have all possibilities for the erasures.
Right.
You copy with all possibilities.
Right.
Yeah. Right.
So this is how we implement erasure code. So basically, we put a single error correction mechanism, but we just doubled it, and we apply it to each word. And we just examine which one actually corrected the value, and we take the value. The important thing is this latency almost the same as a single error correction latency, right? Compared to 100 cycle or 1,000 cycle, this is a huge win. And the ADM power, we're just doubling a single error correction code. So it's similar to twice of ADM power overhead. So this is also much less than conventional double bit error correction code. So big message is we can correct 2 variability errors in one time. And we can also detect another bit errors, which is a case of soft error. So this is ongoing work. So we are trying,
Can you go back
yeah.
one slide? So I see how this gets you fast SecDed, but I don't see the connection to...
No, this is not the fast SecDed.
All right.
We take an existing SecDed,
Yep.
but we are making that TAD as a similar.
Yeah, I understand, but I'm just... Okay, got it.
Yeah. So this is ongoing work. So real overhead of erasers, we have to store the erasers, right? So for this word, we know this bit is wrong, right? But there's a way to detect the erasers in the runtime. This is one case. So what we do is we just examine bit lines from each cell. So there's only 2 valid patterns, 0, 1, 1, 0. That's how we read the value. But if we get the old 0, 0 value, that means this is a slow cell. And if this is a different 1, 1, then there's it consumes too much power. So basically, we are deploying the latency of this circuit. So if this works, then so we can detect erasers in one time during in field. So final picture with the 2D coding is we put a fast detected code as horizontal code, and vertical code is just a simple error detection code. So we are assuming many defects and single bit soft error. So we only repair larger scale variability errors using redundancy. Then during runtime, fast detected will correct up to 2 variability errors. Then if you for example, if you have a soft error, it becomes a large scale errors. Then 2D coding will take care of those errors. So we are working on this one, this array to tape out our prototype in the winter of this year. So we are using 9nm bulk process. So summary of 2D erasure coding is we can use 2D coding idea to provide variability tolerance. And by doing this, we get higher yield or higher performance or low power, right? So let me just briefly go over the related works. So there has been proposal to use multiple error correction code for either multiple soft error or variability errors. For most of them, they actually use error correction, multiple error correction code as they are. So it taking much latency or power. There's another way of another proposal. Group of proposals to duplicate value in different places. It can be duplicate in L2 cache, for example, or it can duplicate in another array. But it actually requires extra area, or it takes lots of bandwidth and power. And also, it needs multiple error protection at the other array. So variability tolerance, there has been some recent work which statistically model and do the circuit simulations and do the Monte Carlo analysis simulation to get the variability model. So basically, we are showing similar problems for the future. And there's a lot of techniques to mitigate variability errors. And obviously, we can use existing single bit error correction code, but we lose runtime reliability. Also, we can apply a lot of redundancy, right? Line redundancy or array redundancy, or we can disable memory, right? So recent proposal disable like more than 50% cache to save only power. Right? There's a bunch of techniques to use a non-standard cell structure or circuit technologies, but again, if this achieves something, we can apply to our technique to improve further. So we are not actually contradicting these techniques. So let me just go over what I have been doing and what I'm going to do for the future. So I spent a long time in Carnegie Mellon University to develop full system simulations to do the research. So we're pretty proud of these full system simulations. And I basically worked on reliable architectures. So at some point, I worked on developing reliable processors. So using redundant multi-threading or redundant processor cores, and then using reducing the comparison bandwidth, something like that. I also applied memory RAID technique to survive from node failure in DSM server, which contains many memory nodes. So it was like some effort from operating system too. Then for this talk, my latest work is 2D error coding or erasure coding to get the multiple error tolerance or variable error tolerance. Yes?
When you say DSM, you're referring to distributed shared memory?
Yeah.
Okay.
Yeah. So what I've done for this is when we lose one node, we guarantee that. All right. Okay. Yeah. Distributed shared memory server. So I'm currently working on this part to get a prototype chip and then trying to see the potential improvement, validate the potential improvement. And so for my future work, I'm interested in. So my view for future processor is should allow easier design, easier testing, easier manufacturing, or easier repairing. So for those one, I'm assume a fully distributed architecture with programmability and some reconfiguration support. And I'm still assuming a multi-level protection in different granularity. Also, I'm still interested in full system simulations, right? So as we go to multi-core, we still have the problem in accuracy and latency of simulations. So these, in CMU, we're spending lots of time to bring up hardware and software core simulations, and I'm very interested in that one too. Also, I'm interested in flash memory or the virtual machine technologies to get the optimal resource utilizations. So that's another area I plan to investigate for. So conclusion of this talk, I showed that why we should worry about the memory reliability and manufacturability. And I propose a two-dimensional error coding or fast multi-error detection code to correct soft errors and variability errors in a field at very low overhead. So that concludes my talk, and I'll take questions.
So can this technique be used to increase the reliability of memories that use multiple voltage levels to increase storage density?
Yeah, of course, right? So even for any kinds of even for multi-level voltage or whatever, it will be manifest as errors, right? Randomly distributed errors, and at long tail. As long as we have a distribution with long tail at the end, error correction code is a very good candidate because it takes most of the cases using a small overhead.
Are you thinking primarily of flash, or are you asking about DRAM as well?
I was actually, more I didn't think of the flash, I was asking about more.
Actually, I can talk about flash too. So what I'm...
But I mean, flash is natural.
Yeah. So flash, actually exactly the flash, right? So to get the multi-level solve, we have to do the, we have to make a stereo distinction between among the voltage levels, right? For that, but still, we have a huge problem on variability over these levels. So these days, mass product flash has only up to like a 2-bit MLC, right? So I'm actually interested in using my technique to get like a 4-bit MLC or something like that. Yeah. Any other question?
I have one other quick one. So, you know, you're applying most of this work to SRAMs, and in particular caches.
Mm-hmm.
And
yeah.
it seems like you could partition caches into, or when you read cache data, you know, if it's clean, you really only care about error detection because you just flush the pipe and
Right.
read it from memory.
Right.
And if it's dirty, you really want to care about error
Yes,
detection.
that's true.
Right? But much of the data in your cache is either dead, very little of the data in your cache is still alive and dirty.
Actually, that's 100% correct for soft errors. For variability errors, it's not really true because we are randomly introducing errors, right?
Right.
So even for clean data, we have to correct it right away. It's not just about detection. We have to correct it if this is used for variability errors.
Your solution to timing variability is about memory. Couldn't help, right? Just
What's that?
Well, if your solution to a slow cell is to go out to memory,
Right.
you haven't helped yourself.
Yeah, I'm thinking about soft errors.
Yeah, soft errors. Yeah, you're right. Also, it's not only about cache, right? For example, for variability errors, we can actually twist it. So I only show that 4 different design points, right? The slow, read latency, write latency, or stability. But it can be change it by adjusting transistor size of each cell. For example, if we are going to use this one for, say, store queue, timing critical, you can actually make a transistor to more vulnerable to other than a timing.
Yeah.
So something like that. There's some potential to use for different memory structures. Right. Actually, we are trying to model store queue and L1 cache and L2 cache as 3 different cases we're using to decoding.
You don't typically think of your store queue as time critical, right?
Okay, then issue queue.
Okay.
Yeah. Or register file.
Any other questions? Should we let him off the hook? All right. Thank you very much.
Thanks.